it comes to visual data or visual models, convolution was also one of the ideas that people tried to use it in order to do generation, or in order to somehow realize one autoregressive model. And they actually used roughly the same way as we did it with transformers. And to just impose that autoregressive behavior, they just use the idea of masking. This is the whole purpose that we have it here, to understand what does masking mean. So what we want to do now, we want to work with visual data. And since we're working with visual data, it somehow sounds natural that we just work with convolutional layers, right? But the issue with the convolutional layer that comes immediately into your mind is that you essentially are not extracting context, right? So recurrent network going to go through every pixel and extract context through history, but this is not the case in convolution, right? So the key point here is that if you think about the transformers in chapter 1, they also did not have any memory, right? In the sense that we have in RNN, right? So essentially, transformer was a bunch of linear layers with those self-attention mechanism, which was a bit weird, but there was nothing like memory in that. And that was just going up, right? And because of that, we were able to do the whole processing in parallel, right? So if we could do this with transformers, why we couldn't do this with convolutions, right? And this is essentially something very well established. The idea of doing the same thing as we did in transformers using convolution. And we basically only need to add a mask to the convolution. So let's look at this together. First, let's see how we can generate one particular distribution if we want to only use convolution. Okay? So say this is one image, like one channel image, and then what I'm doing, I'm focusing on one particular pixel here, right? If I want to generate that pixel, I need to know its distribution, right? So say this is one 8-bit image. So what kind of distribution does it have? It's going to be a multinomial distribution, right? So it's going to have 256 different values. The chance of pixel being 0, pixel being 1, pixel being 2, till pixel being 255, right? So I need 255 different numbers which are looking like a distribution, right, for every single pixel. So if I want to generate it for this pixel, and if I right now only think about generating it, I don't care yet whether this is really autoregressive or not. So what I'm going to do, I'm going to take a convolution filter, so one kernel, and then I put this kernel where, say, that pixel is in the center of the kernel. So that kernel is looking on the pixel and everything around it, right? And then it computes the convolution, right? So it has a bunch of weights, multiplies it with the pixels inside the image, adds them up. It's going to be one single number, right? And I'm going to call it Z1. So if I use one kernel, I'm going to make one Z1, right? And then I need 256 of them, right? Meaning that I can take the second filter, one other kernel, and do the same thing at the same point, another kernel at the same point, and so on till the last kernel, right? So I just need 256 different filters, convolutional filters. And once I put that filter exactly on the position on this image, which is centered at the pixel, then those guys together are going to compute 256 different numbers for me, right? Now, I have 256 different scalars. I can look at them as logits, and then I can pass them through softmax, right? If I do that, if I pass them through softmax, then essentially I'm computing one distribution for this particular pixel, right? Do you agree with me? So what I'm computing is a distribution, right? And this is distribution for that particular pixel. Why? Because if I want to compute it for the next pixel, I can take all of the filters and shift them to right, right? Like the convolution you do in CNN, correct? So in CNN, what you do, you start from top left, and then you keep on scanning the whole image, right? So what you can do here, you can do again the same way, right? And the only thing you need to have 256 different kernels. And then essentially, you're going to compute distribution for every single pixel, right? So we are able to use the convolution to compute distribution for every single pixel. That's good. But one thing that might come to your mind here is that when we are looking at this receptive field, and by receptive field, I mean when I'm talking about this blue pixel, the region on the image which is contributing in computing the probability, the distribution for that pixel, okay? So that red window here, okay? If you look at this red window, it contains not only the previous pixels, but also the pixel itself and some future pixels, right? So assume that I'm doing autoregressive modeling, meaning that I'm going to generate the distribution of the first pixel. Then for the second pixel, I would say distribution of the first pixel given, second pixel given the first pixel, right? And then for the third one, it's going to be third one given first and second, and so on, right? Now, if I do it like row-wise from top left, so I'm going to go like this till here I get to this pixel, right? Now, when I am computing the distribution for this one, this should be conditioned to everything before, right? Everything that I have already seen, correct? But this window, this receptive field, is not looking on only previous guys. I mean, there are a bunch of previous guys here, this one, this one, this one, this one. But those guys which are on bottom or right, these ones, these three on the last row, and this particular one on the right-hand side, they are future, right? So I don't want them to be included in my distribution computation because I don't want my distribution to be conditioned on them, right? Also, I don't want my own pixel to be inside, right? I cannot condition my own pixel to itself, right? Anything conditioned to itself is 1. The probability is either 1 or 0, right? So the blue pixel and anything after that, they should not be inside, right? So this is one issue that this computation here has. The issue that every single probability that I'm computing is not conditioned in the autoregressive form that we want, right? Everybody's clear? Questions? No? Okay, great. So the issue here is that the receptive field is including the pixel itself and a bunch of them after that. And this is a problem, so this is not really the conditional distribution that we really want. Because when we compute a conditional distribution in this autoregressive model, essentially we need that distribution to be conditioned to what we had before, right? All of the pixels we have scanned before. We started from top left, and then we kept on going to right and then down. So anything that we are going to include in the condition should lie behind the particular pixel that we are looking to, right? So this is the issue here, and the pixel itself definitely cannot be inside that as well, right? So, but here we have a bunch, the pixel itself and a bunch of pixels from future. So this is not a good idea, but we do know how to get rid of that. And this is essentially just doing masking. If you remember, when you wanted to just generate by transformer, when you wanted to just generate the next token, what did we do? We essentially computed first all the possible connection, right? All of the self-attentions. But then we somehow mask out all of the weights in the future because we didn't want the next tokens decide for our decision at a particular time, right? So when I want to just predict the next token, I don't look at whatever I have in my data, right, in the future. I just look at the previous ones, correct? So that was the idea of masking. We called it mask decoding, and this can be simply applied here. So how can I do that? So this was the filter that I was using to just compute the distribution. So this guy is looking into the pixel itself and some future ones as well. If I want to mask it, which guys should be masked? Center one should be, definitely. The last row should be as well. And then one next to the center one, right? So these are things that I have not looked into yet. And I don't want them to appear in my condition, right? So I can simply just mask them out, right? Meaning that I set their weights to be 0, right? And when their weight is 0, then essentially they are not going to show up in the condition. The problem is solved, right? Everybody's clear? Questions? So this is the idea of mask convolution, and this essentially led us to just always look into the past, and this is a good thing to just use when we want to do autoregressive modeling. So essentially, when you have a mask convolution, you, depending on the way that you are going to scan, but I consider like the classic one. From top left, I start to go right, and then I just come down, and then again go right, and so on, right? So if I want to do that, then essentially I don't want anything from the future to be here, right? So this means that for the second row, the 2 right pixels, and for the last row, all the pixels should be masked out, right? Now, when I am at the first pixel, I am doing a computation. I'm computing the distribution. What is going to show up after doing the convolution? What's going to be the output of this convolution in this image? 0, right? And I'm actually conditioning to nothing because this is the first pixel, right? Condition to nothing, right? Then you go for the second pixel. In the second pixel itself, the one next to it, which is the third pixel, and anything below are masked, right? So when you compute, output of the convolution would be dependent only on the first pixel, right? And then whatever distribution you compute, that is going to be conditioned on the first pixel, right? And you are computing the distribution of the second pixel given first pixel, so it's okay, yeah? So it's just fitting the autoregressive form, right? Same thing when you go next. Here, when you go next, third pixel itself is masked, fourth one is masked, anyone below is masked. The only thing that is going to show up is from previous, right? Is from X, it's actually X2, right? So your output is not going to depend on X3 or anything after that. And you're still conditioning to the past, right? Everybody's clear? So you essentially get the same convolution as before, you only mask the future, right? And what does future mean? It depends on the way that you go over your image, right? So the way that you open your chain rule is going to decide which pixels you need to mask, right? So here in the standard one, I assume I am considering x1, then x2, x3, and so on. And each time I condition to the previous one, so I'm going to do it this way, right? And as you can see, every time that I'm computing something at the right-hand side, that is only depending on the previous one, right? And of course, you do get this point that I am doing actually 200, I mean, in this particular example, I'm doing 256 different of them, right? Because I want to compute a distribution, right? Every single pixel is computing one of those logits, right? And then I pass them through one softmax, right? So you're going to get your 256 kernels, and then you start from the very first pixel. You keep on going. And each time that you do a computation, you see the corresponding computation on the right-hand side, right? So this guy is going to compute the probability of the first pixel depending on nothing, second pixel depending on the first one, and so on, right? So you're going to keep going like this, and you can exactly cover the whole image, and each time you're conditioning to the past, right? So this is doing the autoregressive modeling. Clear? Everybody's cool? Questions? Yeah.
Just a quick question. Like, for example, in this case, we are sort of assuming we're doing with a grayscale image. But what about how does the conditions? How do we deal with the conditions when we're dealing with RGB?
Same thing again, right? So as I told you last time, I'm going to mention it briefly next. But in RGB case, you go for R first, and then green condition to red, and then blue condition to green and red, right? And then you can again design that three-dimensional tensor in a way that you always have this kind of masking. Yeah. So one basic idea is that you take the same mask filter as I showed here, but you don't do it three-dimensional. So no 3 channels, just 1 channel, right? First you do it on red, and then you go inside depth, and then you come out and you keep on going like this, right? And each time that you do it, then you are conditioning to the previous ones, right?
Yeah.
You can do it, but actually do it more efficiently. Yeah. But it's only just to find out how you want to open your chain rule, and then you just make the corresponding 1, 0. Yeah. No worries. Yes?
So in this case, we're actually not conditioning on all the pixels before it.
Great, yes.
We're only conditioning on like several pixels.
Yes, which is not going to be exact. This is why we next go deep. Yes, but right now we're just doing 1 layer. And in this case, we're not doing the exact autoregressive. The only issue that we are resolving is that we don't have the future, right? Yeah. But still, our conditioning is not accurate because as you exactly mentioned, for example, here, or maybe here is better. So here, I am not conditioning x3 to x2 and x1. I'm just conditioning to x2, right? Which is a kind of approximation. So I assume x3 given x2 and x1 is roughly x3 given x2, which is not always correct. Your point is totally correct. This is what we discuss next. Yeah, of course. So everybody's clear on the masking? So how we do the masking? And then once you have done this, then essentially you have computed all the logits that you need. And the only thing that you need to do is to just pass it through a softmax, right? So now this guy can be done in parallel, right? So when I want to compute, for instance, the context for this last guy, I don't care about what I have computed first, right? So it's not I mean, they are not impacting each other. This is exactly the same thing in the transformers, right? And this was why we were able to just do all the computation in parallel, right? Same thing we can do here. Questions? No question. Great. So, as your friend mentioned, the issue with this single mask convolution is that we actually are capturing a sort of short-range memory. What do I mean by short-range memory? I mean that when I'm looking in one particular pixel, the center pixel, which I'm showing by X, I, and L, if I'm looking at that particular pixel, the thing that is happening is that I'm not taking that pixel into account. That's fine. I am not taking any future pixel into account. That's fine. But at the same time, I am not taking into account all possible previous pixels, right? So what I'm doing, I am conditioning this X, I, and L into these guys, these red pixels, right? Which means that my autoregressive modeling is somehow approximate, right? So somehow I am assuming that the distribution of XIL given anything before is roughly the distribution of XIL given anything in the neighboring, right? So this is the kind of approximation this single layer of convolution is imposing on my AR modeling, right? Whether this is exact or not, well, you can guess this is not, right? But you remember we did it in the Bayes, naive Bayes as well, right? So there we just considered a model. This was not accurate. This was actually stupid, but that's something that works sometimes, right? So you can think that this is going to work if we have a very simple task, but eventually if you really want to generate an image, this is not going to work. You can guess, right? Because considering one small convolution, then it's very hard to assume that your particular pixel, especially when your image is very high resolution, is only depending on the neighboring pixels, right? This is pretty much impossible. It's probably a very wide area around that pixel which is going to contribute, right? So how can we resolve that issue? Any idea?
Do more filters, like get more layers.
Yes, you just go deep, yeah? As you go deep, I mean, deep learning says when you go deep in with neural networks, every problem gonna get resolved, right? And this is essentially what we're going to do. So what we want to do essentially, we want to just widen this receptive area, receptive field, when we are computing the distribution for one particular pixel. And the way that we can do it, we can use one deep masked convolution, right? So if you, just as a recap, when we have a deep neural network, the classic convolutional neural network, when you are looking in the first convolution layer, then you essentially can say every single pixel is depending on a tiny part of the previous image, right? But as you go deeper and deeper with convolution, that receptive field is going to get wider and wider, right? So for instance, here the blue pixel only depends on that 3x3 part of the original image, right? But then if you look at this yellow pixel at the second layer, this is going to depend on a 3x3 part of the first feature map, right? And then every single guy inside this feature map depends on a bunch of pixels, right? So if you want to really know which pixels are really related to this guy, you essentially need to just track back every single feature in the previous layer, right? And then that one is going to widen, correct? So meaning that this yellow pixel is pretty much depending on every pixel inside the input, right? Correct? So this is a simple fact. If you go deep with convolution, then essentially you are going to expand your receptive field. And at some point, when your convolution, your CNN is deep enough, you start to have at the input the whole image as the receptive field, right? And this is why we usually say with convolutional neural network that first layers are just looking into the local features, and gradually as you go up, you're looking into the high-level features of the image, right? Because deep layers, they're essentially looking at the whole input from the lens of the previous layers, right? So moral of the story, as we go deep with convolutional neural networks, we essentially can increase the size of the receptive field. So eventually, if we do the same thing with the masked convolution, we can essentially increase the receptive field. And given that each time in every layer we are masking out the future, that receptive field is going to mask out the future as well, right? So we're going to look at the whole image masked to the future, right? So this is going to be the case. So if, for instance, I'm looking at, I'm doing the mask convolution, I'm looking at the very first pixel. Well, that first pixel in the very high layer, so the first entity of the very deep feature map. So this blue map that you see here, assume this is the output of the convolution after multiple mask convolutions, right? So you do multiple layers of mask convolution, and this is the blue map coming out of it. The first guy in the blue map is essentially depending on everything in the input, right? But masked to the future, because every single time that you computed the convolution in every single layer, you just did masking, right? So essentially nothing at the input is going to impact on this guy, right? Because the effective weight of all of them is 0 now, right? By masking. But when you go, for instance, for this pixel, this particular pixel in the output map, so what you're going to see, the previous one was depending on local part. But every single guy which was allowed there, not masked, it was depending on everything before, right? In the previous map, and so on and so on. So your receptive field is just getting expanded, right? So essentially, you can say that if you have deep enough number of mask convolution, this guy is going to somehow depend on anything before, but not the pixel itself and future, right? And now this is the thing that we want, right? Because we want that this value we are computing here depends on any pixel that we have seen before, right? And this is going to happen. Everybody's clear? Questions? No question? So you got the idea of masking, right? So essentially, just mask out the future, and then if you want to make sure that you have enough, you have wide enough receptive field, you just keep going deep, right? And this is going to do the job for you. So essentially, when you do that, then it's going to extract the autoregressive context. So if I can do this, then the only thing that I need to do is to just do this with filters of size 256, right? Then I'm going to get at every single of these blue pixels 256 different lodges. I pass them through softmax. I get the probability that I want. And I don't need to wait anymore like in RNN to compute the probability of every single pixel, right? OK. So this is the idea of PixelCNN. So quiet noun architecture, one of the first visual architectures, giving sensible results on image generation. And it was in the same paper proposing pixel RNN. So they actually came up with this idea that we need to do autoregressive modeling. And they used LSTM and deep mass convolutional neural networks to do that. So this is the way that you do it. So you essentially do multiple layers, so many layers essentially of convolution, and all of them are masked. It means that the pixel itself and the future pixels are masked out. One tiny thing, typically when you do masking, you're going to mask the filter itself in the first layer, but in the next layers you don't need that. Because essentially you can show that if you don't mask it in the future layers, still that pixel is not going to leak into the context you compute. And because of that, it's OK to keep it there, right? But at the first layer, you need to mask the filter, the pixel itself as well. But anyway, this is a very tiny thing. So you can do the masking up to that point. And essentially, you are going to compute at the very end one big tensor with 256 different channels. Every single of those channels is giving you one of the lodges, right? And then you just do the softmax. So just a few notes here. First of all, this architecture, it typically needs to be very deep because you can guess. You need a very complicated model if you want to generate something, because this is a very hard task. And at the same time, you need to go deep enough to make sure that you have wide enough receptive filter, which is going to make your autoregressive modeling accurate, right? So this is an important thing to just look at the problem from both sides. So not only computationally advanced model, but at the same time, you need to have accurate autoregressive modeling. This is important. The other thing is that you see this connection here, right? And what do we call this connection? This is skip connection, right? Why do we use a skip connection? In ResNet, for instance? Gradient, right? You don't want to see vanishing gradients, right? So same thing going to happen here, right? Because it's very deep, so you essentially are very vulnerable to vanishing gradients. So you need to use skip connection. So in the original proposal, a skip connection was there. And not only a skip connection, they also used the idea of gating as well. Those of you who had some experience with LSTM, you know that gating to resolve the issue of vanishing gradient, right? So they used both the ideas to get rid of this vanishing gradient, because if they wanted the whole architecture to work, they needed it to be very deep. So this is the next thing. And the last thing, as I said, so last layer, last output needs to have 256 different channels, right? And then because you need to compute the softmax out of it to have a distribution. Okay? Questions? No? Yes?
So for previous layers, not the last layer, you only need like one filter, right? Like for each layer, or do you need like?
I mean, essentially, you're going to use much more filters because you want to have so many, features, right? But if you're asking from the validity of the model point of view, you're right. I mean, you can't. This is the last layer who needs to compute lodges for you. That's correct, but I mean, doing one filter, it's not going to work, right? You can guess. So, questions? No question? Great. So now, let's say that we want to just have this pixel CNN. We want to train it. What should we do? We should do How do we train a generative model? Maximum likelihood always, right? So maximum likelihood, no doubt about that. So how can I do it? So, okay, I'm in one particular epoch that I'm doing the training. I'm going to collect a batch of images, right? And then when I collected that batch of images, I go in for every single image, right? And I process it. Now, if I want to do the processing, should I do anything in sequential form? No, right? I'm going to get that image, pass it through this masked CNN, and at the output, I'm going to have, in one shot, the whole distributions, right, that I want. Correct? Because looking at this architecture, the image is going to be here at the input, and everything is going to be computed as a normal CNN. And at the output, after softmax, I'm going to have one big map, including all the probabilities, right? So that's what I'm going to do, right? So I really don't need to do any sequential processing anymore. I get every single pixel, and every single image, and pass it through the mass CNN, right? And for everyone, when it comes out, I'm going to get all the probabilities. So I'm not going to compute P1, then P2, P3 till PD. I'm going to get P1 to PD all together, right? And this is the whole parallel computation that I'm gaining here, right? So I get this guy. Now that I have this one, what should I do with that? Should I use it to sample anything? No. Good move. I mean, you got my training. So what should I do? I have the ground truth, right? I know what is the value of every single pixel, right? So I have computed this probability distribution, which is 256 different values, different probabilities. I'm going to see what is the pixel. I take the corresponding probability. That is the likelihood, right? I compute log likelihood, and I just try to maximize it, right? So the next thing that I'm going to do, I compute the log likelihood at the ground truth that I have. This xij is the value of the pixel. And look at this value. First pixel is 0, so that whole vector, I don't need it. I just take the first probability, yeah? That is the likelihood of the first pixel. Likelihood of the second pixel the same way, and so on till the last one, right? So I'm going to compute these ones. This summation is going to give me the whole likelihood of the sample. And then I average it over the whole batch and update my weights, right? And I keep on doing this till my model gets trained, right? Then finally, I'm going to return the trained model. That is a model which is supposedly capable of generating one image from the data set that I have trained my model on. Questions? Everybody's cool about the training? Now, if I do the training like this, now how should I generate one image? So I give you that weights of the mass CNN. How you can use that mass CNN now to generate one image for me? Can I generate the whole picture at once now? No. Yeah, good move. Great. So well, I should do autoregressive generation, right? Meaning that I should generate first the first pixel, right? If I want to generate first pixel, what should I give as the input to this model? Nothing, empty, right? I'm going to start with empty. I'm going to get the first pixel, right? And a bunch of other pixels which I don't need, right? Then I get the first pixel, put it at the input. Now my input is first pixel, everything else empty, right? I'm going to generate once again, pass it again through the mass CNN, and then I'm going to get first pixel as before, second pixel, and a bunch of future pixels, right? I'm going to take those two guys, put it again in the input, and I generate the third pixel, and so on till I'm over. So I cannot get rid of autoregressive generation in any way, because this is an autoregressive model. Yes?
Yeah, so for meaning empty, you mean like 0, basically?
I mean, it depends, as I said last time, it depends how you define the empty. Yeah? You might define that I give like a complete blank image, this is an empty. But when you want to give empty, you consider the same way in your training, right? If you're in your training, when you do the masking, you zero everything out, then essentially empty means 0. Yeah? But if you do anything else, then you should do the same thing. So it totally depends the way that you have done, right? Okay, so if you want to generate, you must do it autoregressively, and then you start with x0, which is essentially empty. You just sample the prior to get your first pixel, right? You pass it through the whole mass CNN. You're going to get all the pixel distributions, right? But you don't care about the future ones because they are essentially nonsense yet, right? You're going to take your first pixel, right? So you're going to take P1 and you sample by P1. So I'm going to get P1, take one sample from it. It's going to be my X1, right? Now I'm going to replace X1 in my previous map, which was essentially empty. And now I have the first pixel, anything else empty, right? Again, I pass it through the mask CNN. Now I'm going to get P2, right? Now that I have P2, this P2 is essentially the distribution of the second pixel given the first pixel, right? And I'm going to sample from this, fill it into the image, and I repeat this. I keep on going till I end up with all the D steps. So I have generated all the pixels, and now I have my whole image, right? Everybody's clear? Questions? No questions? So you cannot run away from the autoregressive generation. That's downside we're going to take because we are, we have the luxury of simple sampling. But for training, we can do it in parallel if we use right architecture, right? So autoregression is not something essential for training, but for generation, you always need to do that, right? So that being said, now you might guess that you can do it more efficiently if you use transformer, because transformers are known to be the best ones when they want to just, capture long-term connections, right? Because of self-attention, and this is totally right. You might be now super sad because you would say, okay, he is going to start again talk about transformers and show us again training and sampling of the transformers. But good news, I'm not going to do that. Because essentially, if you want to generate any image with transformers, you are going to do the same thing as you did it in the language models. It's no difference. Because transformers do not do any special weird kind of convolution, right? So they are just doing MLP kind of computations, which is going to be the same everywhere. So essentially, when you are dealing with your transformer, you can think of your image, for simplicity, to be a sequence of tokens. And tokens are essentially the pixels that you have. And then you give it to your transformer-based autoregressive model or transformer-based language model to generate the next token, which is the next pixel, right? And it's going to start with empty and then generate the first pixel, second pixel, and so on, right? So we're going to have exactly the same architecture. We're going to do a bunch of embedding at the input to get the pixel and represent it with a bunch of numbers, which we can use it to compute keys and queries and values. And then you need to do positional encoding as before because you want to know that this is pixel at point 1 and 2, right? So you need to do the positional encoding. So this positional encoding is essentially embedding the position of your pixel, that I and L, for instance. And once you do this, then you are going to pass it through L different layers of transformer, right? And in every layer, you're going to do masked self-attention. And you do now why we do masking, right? Because we are doing autoregressive modeling. We don't need the future, we just need the past, right? So we're going to do mask decoding here, mask self-attention. Each time you're going to pass it through one linear layer for extra computation. And then once you keep on doing it for multiple times, then you have at the very end a very good, set of processed values, right? That is the output of your last self-attention layer. You probably pass it through one other layer, and what you get here is exactly the logits again, right? So if you think of the image, that very large image, for every single pixel in that image, you consider that to be a token. And for every single of those pixels, you have now 256 different values, right? You pass all of them through softmax, and you're going to get the distribution of your pixels, right? And again, exactly like the mask convolution, you can do it here in parallel, and we have seen it before this, right? So in chapter 1, we have seen that we essentially don't need to do any sequential processing with transformers anymore, right? So same thing is going to happen here. Questions? No question? Okay, great. So as I said, when you think of visual transformer-based autoregressive models, you can always think as it is one language model, and then time is going to be position of the pixel now, and then the token is essentially to be the pixel itself, right? The value of the pixel. Okay, so one early example of that was ImageGPT, which was somehow tried after GPT-2, somehow showed quite nice performance. So that ImageGPT was, I mean, the title of the paper is essentially just looking at the, pixels as tokens. This was the title of the paper. Like, you just look at the pixel as tokens, and then you just process them. Then you see that you are able to generate image. So, few notes here. First of all, when you think about any transformer-based autoregressive visual model, then we would say, okay, every single token now is a pixel, right? And if we think of 8-bit images, then essentially it means that every single token has 256 different values, right? So inside your vocabulary, you have 256 different values, right? The case where pixel is 0, the case where pixel is 1, the case where pixel is 2, and so on till the last one, right? And you're going to embed or represent every single of these tokens with one embedding, right? So this is the simplest way that you can think of, but typically in practice we do patch pixels, right? Like the one I told you initially. So you are not going to just consider every single pixel to be one token. You would say, okay, every bunch of them are one token, right? And then you can now imagine that the number of tokens you have inside your vocabulary is going to be larger, right? Because if I have two different or two neighboring pixels together to be one patch, then essentially the number of cases is going to be 2 to the power 16, right? And so on, right? If you have 4, then it's going to be 2 to the power 4 times 8, right? It depends on how many pixels you put in your patch. So when you do patch pixels, then you have this option to do tokenization. And it's good to think about it, why we can do it. Because it's true that you have lots of possible cases to be together, but for many images, you know that many pixels together do not happen, right? So when this pixel is absolutely bright, the other one is not going to be absolutely dark, right? So it's going to be, if it's a normal image, it's going to be a smooth transition from bright to dark, right? So this means that it's true, for instance, for 2 pixels together, you have 2 to the power 16 different cases, but many of them are not happening, right? And if this is the case, then again, you can just represent your patches as tokens. Then you can go over the whole image as the corpus, and then you do tokenization by getting rid of those cases which are not happening. Then you reduce the size of your vocabulary, right? So you can do this again exactly as we did it in the language models, because essentially visual models are somehow representing some context in the visual form, right? And not every possible combination is within that context. So this is one of the things that you can do. You, of course, do the embedding, and this is the point where it gets interesting, because when you get your pixels, like you think you are doing pixel patch, right? And then I have one patch of pixels here, and now I just do embedding for it, right? And I don't need to represent this whole thing with a very large vector, right? I can represent it with a small vector, because as you remember, when we just write down the embedding, we don't necessarily have the same embedding size as we have the number as the size of the vocabulary, right? So you can represent it with a smaller vector, right? And similar to the language models, where every single embedding at the end is somehow showing where the word is lying depending on its meaning or its context, same thing is going to happen to your pixels. So it's going to say these pixels together are here, and some bunch of other pixels in your image are again lying around there, right? So they're going to have the same embedding, close embedding. And because of that, this says this part of your image is somehow related to this part of your image. Now imagine you are considering like image of a shirt, and then the whole shirt is not there. So a part of shirt is on the right-hand side of the image. Another part of the shirt is on the left-hand side of the image, right? But they are both parts of the same shirt, right? With the same color and same properties, right? So then, essentially, if your model is trained very well, then this patch of the right-hand side and the other patch on the left-hand side going to have close embeddings, right? Whereas the center patches are not having the same embedding. It says that this is shirt, this is also a part of shirt, right? So you got the idea, right? So here, embedding is going to help us just represent with numbers those contexts inside the image, and this gives us some sort of numerical representation of image patches. So one particular thing about the transformer-based visual model is that in the convolution, when we do mass convolution, then we use the fact that this is a convolution, right? And the convolution itself is going in a specific form over the whole image, right? And each time is using exactly the same weights, right? Why do we do that? Because, I mean, essentially the whole convolution comes from the fact that we know this is a visual scene and it's going to have some sort of common properties in it, right? So convolution by itself, by definition, it is having some sort of spatial coding in it, right? So when I'm looking at this part of the image, I look with the same weight as I'm looking at this part of the image, right? So convolution itself has a sort of spatial coding in it, which is very well or specified for the visual images. But this is not the case with self-attention, right? So self-attention is just treating it as a bunch of tokens, right? Now, eventually, at some point, it's going to get this spatial correlation as well. So it's going to start to understand the spatial pattern inside your image. But this turns out that you typically need more data if you want to train those transformer-based models, because they need more time, more samples to start getting this spatial correlation. And once they get this spatial correlation, they are going to outperform convolutional-based, because convolutional mass convolutional networks are essentially specifying one specific spatial coding, and then they are just following that. Whereas transformer is capable of adapting to the spatial coding that you have inside your image. So this is one particular point where you do basic experiments. You might need more data and more time to start capturing the spatial pattern inside your image with these kind of models. So if you are interested, you can take a look at the ImageGPT paper. I mean, given that we discussed the GPT architecture quite in details, transformer-based language model, then you can simply capture what they are doing there as well. So just to wrap up quickly what we had for autoregressive models. So autoregressive models are going to just make it computationally feasible to sample. But the cost is that we need to just do autoregressive sampling, which is quite slow. We can do these models by using RNN, but the issue with the RNN is that for training as well, we need to do autoregressive. This is very bad because we cannot do parallel processing, right? But the other form is to just use masked networks, right? Either masked CNN or transformer-based architecture. They just use masking to make it precisely autoregressive modeling, but they do not need to really compute any explicit state. Because of that, they can do the processing in parallel. right? So that's it. One thing is that for visual data, for a very long time, I mean, still now even, many people believe that they are not, autoregressive models are not a very good option because essentially they are slow in sampling, right? If they want to generate, it's going to take a lot of time. But nowadays, again, some research is paying attention to that because it seems that there are some ways that we can get rid of, not that we are not doing autoregressive, but we can do it more efficiently. So given the advancements that we have right now. So questions?